Yes, the quiz was the easiest quiz you'll ever get. I think virtually everybody, I think got a 10. I'm not sure, because literally the input was the output.
Yeah.
All right, the output was the input. All right, now, Wednesday you have voted on the test, right? I want to make sure everybody's aware of it. I put it on OneNote. I want to make sure there's nobody that says, I didn't know. So what I wanted to do today was do a bit of review. And there are basically four major topics. The first is, and I'll go through these, you don't need to write this down, just listen. The first is going to be convolution. And you know, convolution is something where find the one that has the most going on and don't flip or shift it. Leave that alone. Then the other one you're convolving it with, flip and shift, and you have to look over where both functions overlap in the time regime, and then you have to integrate the product of the two. And I'll be doing that. Convolution, in my opinion, is the most difficult concept because it's something that a lot of times, especially functions that have that are on forever, when you flip and shift them, it becomes, or they're skewed, it becomes difficult to see where the overlap is. And I'm just saying this as a matter of practice. I've seen this happen many times. After that, it's Laplace transforms. Now, Laplace transforms are both the forward Laplace transform from the time domain to the S domain, and inverse Laplace transforms from the S domain to the time domain. That's primarily something we use for circuit analysis because we solve the problem in the Laplace domain and then we take the inverse of it through partial fraction expansion and get the actual time domain functional form, the observable form. The third thing will be Fourier transforms, both the forward Fourier transform and the inverse Fourier transform. And the thing about Fourier transforms that make them so powerful, in my opinion, is using duality. And I've talked about duality a lot. And for duality, think of the pulse function and triangle functions primarily. And then from there, you can usually build whatever you want. Any kind of a waveform is composed of those primarily. And I think you've done a series of problems with those. And most people, I think, have a good handle on that. Then Fourier transforms is something we use that a lot when we do DTFT and then finally DFT, and you're going to get it with FFT and then the Z transform, and we're going down that direction after this exam, and then for filtering. After that, there's Fourier series analysis. A Fourier series analysis, again, requires the function to be periodic, and it's something where the analysis allows you to see how each value, say, harmonic, there's the first harmonic, what the signal strength is, and if it goes into a filter, what the output of the filter would be at that frequency. Does everybody understand that? And we use that for circuit analysis a lot. So those are the major topical areas. Now remember, operational amplifiers are part of a lot of Laplace transform work, the realization. And there was a realization 1 and 2, if you recall. So there's a lot more to this than just those, there's the sub areas under them. But if you've been keeping up and doing your homework and making sure you understand it, then you're ready for this exam. The cramming for it is rough, this one, because it's got a lot of different things that aren't directly locked together. Like convolution, even though, yes, you can make the argument if you do the Laplace transform of everything correctly, then you can do the convolution of the product of two functions and then the inverse. But still, when I give you functional forms that aren't readily definable mathematically and I ask you to convolve them, you're going to have to convolve them. And if I ask you to do convolution, it doesn't mean take the Laplace transform. So make sure you don't do that. So with that, before I start, does anybody have any other questions? Somebody made a comment to me, they sent a comment, they'd like to see all the quizzes posted. Yes. First, I've handed back all your quizzes, have I not? All right, you have your quizzes. I think those quizzes, I think pretty much I've gone through the solutions of most of those things. They were either homework problems that were modified, maybe something, or the solution was posted. But if you want me to, if there's a specific quiz that you don't understand or want done, let me know now. And I'll try to address that, because I'm not sure whoever sent that what you were getting at. All your quizzes were handed back, weren't they?
Yeah.
All right, I just want to make sure about that. All right. So now, any other questions at all? All right, let's start with convolution. So we know when we have two functions, if we're going to convolve them, I'm going to say y of t is x of t convolved with h of t. Those functions could have an infinite extent where they're non-zero, they could be finite. There's a lot of things that could happen. Now I'm going to show you a couple of things that I think are most tricky, in my opinion. The first is, if the first function you have, I'm going to call this x of t as something like this. If it's something that is like this, and call this, I'm going to give this a hard number, 1, and call this 3 with a height of 1 and a height, yeah, that's a height of 1. So that's my x of t. Does everybody see that, class? Now my second function, I'm going to do this. I'm going to see my h of t here will look like this. And call this 2, make this 2 here, 1, 3, and this is time, and this is time. Now here's a difficult choice. Which one do you want to flip and shift? This is my opinion. Anytime you have a square block and another thing that's actually varying with time, flip the square block. That's me personally. It's up to you what you want to do, but that's what I would do. So with that in mind, I'm going to leave h of t alone. Do y'all agree this is a fair thing to ask? I mean, you realize you've done problems like this, and I want to make sure that there's nobody that doesn't understand how to do this. So if we're convolving them, first the definition of convolution, you may be asked, but convolution is really going to be the integration technically from minus infinity to infinity of x of tau times h of t minus tau, d tau. Now, you can use lambda. Does the book use tau most of the time or lambda?
Pretty split, half and half.
It uses tau? All right. It doesn't really matter. It's a dummy variable. By that, I mean after the integration, it's gone. It's just a variable that's used to capture the integral, right? It's not going to exist after this integration. Can you all see this, by the way? Far back? All right. So I'm going to leave this one alone. So here's my h of tau versus tau. And it looks like this. All right. Now I have to take this one, and first I'm going to flip it. So after this, I'm going to flip this one. Of 1. And this is my x of t, or x of tau, minus tau. Does everybody agree with that so far? Now, what I'm going to do, remember, that's at what? At t equals 0. Isn't it, class? I haven't added t inside there. Now, as I add t inside there and go pause, and by the way, y'all agree for times less than 0, there is no overlap here, class? Yeah. Everybody see that? So, and there's no overlap here, and it's not going to have overlap until t is 1, right? So, but now what I'm going to do, if you don't mind, I'm going to erase this and just move this one down. And I'm going to, because it'll make it a little easier on me. So now I'm going to do this. I'm going to say, this is going to be x of t minus tau. And here, this is t. And therefore down here, it's the width of that is 2, so it's going to be what? T minus 2, right? And here, what am I going to say? This is for t greater than 1, right? You all agree? At t equals 1, where is it? Right there, right? It's just starting to overlap. How many see this right here? Everybody? All right, now, think about this. That's 1 there, right? 2, 3. So from 1 to 3, we're basically getting more and more overlap. Do you agree with that, class? And I need an equation for this in terms of tau. So the equation for this would be what? It would be simply tau, right? H of tau would be equal to tau, and this would be for tau between 0 and 2. It would be 0 for any other value of tau. Do you all agree? Everybody see what I'm doing here? I need an equation, is what I'm getting at. Are you with me? You're gonna be asked to write equations for lines. You'll have to know how to make an equation for a straight line, no matter what its zero intercept is, or what its slope is, or something, you know, that like an exponential decay, something like that. You'll have to be able to make give a mathematical description to do this. So now when I look at this, then the area of overlap for this is obviously here and here. And then you take the product of this function times that function and integrate, correct? So, and I'll do this over here. So now I'll just put down for t greater than 1, less than 3, my y of t here will be equal to the integral, and it will be from where? 0 to t, right, of simply tau d tau. Do y'all agree with that? Show of hands here. Do y'all agree with that? Because really, that's the product. And it's really integrating this times this, correct? So what's that going to be? That's really tau squared over 2 evaluated from 0 to t. You agree with me, everyone? Show of hands if you agree. I'm not trying to bore you with this, I just don't want too much complication when I do a shift, so you can see how to do it, right? Now, after that, I evaluate it, and what do I get? Simply t squared over 2 would be y of t, and this would be for t between 1 and 3. How many see this? Agreed? Now, the next part is this. Let this thing, this car, you might say, this cable, more like a railroad car, move through, and now when t is greater than 3, now this is outside that area, right? And now the back end is starting to get less and less covered, so I'm going to try to draw that too. I'm trying to just all draw it right there. I was going to cover the whole board, but I think it would be better just to do this. So next, I have this. This is still t, and this is t minus 2, right? That's still 1. And now I say for t greater than what? 3, less than, class? Think about this. 5, right? Isn't that right, class? Because it can move through 2 values, right? 2 seconds. Agree? So from there to 5, my y of t is going to be the integral from where to where? You help me now. Come on, guys.
T minus 2 to 2.
Yeah,
Say it right. T minus 2 to where?
2.
2. Thank you. Very good. A lot of mistakes on this part right here oftentimes. They'll put it to t. Trust me on that when they do. All right, now what's that going to be? That's tau, right? Still, it's tau d tau. And that's tau squared over 2 evaluated from t minus 2 to 2. Is it not, class? At this point, it's really over. You're just plugging in the upper and lower limits. And I can do that. I can say, therefore, y of t here would be equal to 1/2. And then it's going to be 2 squared minus the quantity t minus 2 squared. Now, at that point, that's the right answer. You can simplify it, and I may ask for a value at t equals, you know, you've got regimes from 1 to 3 and then from 3 to 5. I might say, what is the value of y of t at t equals 4? Then you would have to plug in 4 there. Follow me? And you would have 2 squared minus
2 squared.
Yeah.
which is
0.
at which bug was starting to bug me because that doesn't look right. No, that's right. Well,
Wouldn't your limits technically be t minus 1 and t minus 3 on that diagram you've drawn there?
what's that?
Isn't the leading edge of that block t minus 1? The trailing edge t minus 3?
No, this is,
No, it's t and
Sorry.
t minus 3 calculated.
-1?
oh, I see what you said.
Would that not adjust it to
You
where-
say if you want an equation for this, it would be u of t minus 1 minus u of t minus 3. And so these would become,
that second equation you've got there would be if your x of t started from 0 and went to 2.
You're right, this would, actually, this would be,
So you need to time shift your solution by a second.
yeah, that would be t minus 3, not that. You're right, it is t minus 3, that's right. My bad on that one.
I mean, the solution should look similar. It should just offset it by 1 unit.
What should actually happen is this is basically a shark fin.
Yeah.
It'll be close to a shark fin. Yes, sir.
Why is it t to t minus 3 if the block is only 2 units wide?
Now, this one, the thing is, this is t minus 1 here. All right, it would be t minus 1. All right, and if you do it this way, I didn't want to do it this way. If you write this equation, all right, then you put in tau for t, and then minus tau. U of minus tau minus 1, u of minus tau minus 3, which really boils down to it's going to be tau plus 1 here and tau plus 3 here. And then you see how that shifts. You'll get the region. It's t minus 1 is the lower end, and t minus 3 is the lower end, t minus 1 is the upper end for that one.
So for the first section, the t is greater than 1 and less than 3, would your bounds be 0 to t minus 1 instead of just 0?
That's still going to be, if you look at this, what I did was I took the 1 second off of that already. If this is t minus 1, I've already shoved it through, so now I'm just looking at the area of overlap, and it goes from 0 to t. I believe. Now you got me thinking about that. If I do that, let me just see for a second. I've learned this lesson long ago. Make certain about these things. This is going to be minus 1, this is minus 3, and this is right here, that's x of t minus tau, right? Correct? Now, if I go ahead and I make this t minus tau, that's still, this limit right here is going to be basically t minus 1, and this is t minus 3, following that, right? Now, when t goes to 1 second, it's right here, right? And then, actually, I can do it that way. Now that I think about it. What I can do is say now, this limit is still going to be t minus 1, and this is t minus 3.
So that should be.
And then, this would be from 0 to t minus 1 right here. That's right. That was my mistake. You're right about that. This should be from 0 to t minus 1. And what I'm doing is saying that the limit here is always t minus 1 because of the shift. Which means this becomes simply t minus 1 squared over 2 would be y of t from 1 to 3. That was my bad on that. Sorry about that. But this is one of those problems where what people do, and I'm just going to tell you the problem, they will flip and shift this one, all right? So they get an equation for this right here, and the equation for this is just t times, and you could say it's just t, u of t minus u of t minus 2. And that's an equation for that. Then they put in tau, and then they flip it. By flipping it, you would have minus tau, u of minus tau, u of minus tau plus, or minus t, minus 2 right there. They'd flip it and they'd shift it. And then their integrations become progressively more difficult. That's the problem with this. When you have something that when they flip and then shift it through here, now you got a line like this that you have to write an equation for as it's moving, and you're going to get a lot of problems with that. That's what I'm just warning you. So that's why the square one will leave alone. Yeah?
So why is the interval from 1 to 3 instead of 0 to 2?
At 0, there is no overlap, is there?
Yes.
So, and by the way, I didn't say this, but for all time, outside, only between 1 and 5 is there any non-zero values for the output. All other values are 0. That's the one thing I should say. All right, that's convolution. And here, these are two functions that have a finite duration, right? And one of they both, you know, you could make the argument of flip and shift the triangle. You could do that, but you're going to run into some more difficult problems mathematically. the one that's got a slope to it or an exponential kind of try never to do the flip and shift on that one. I want to do one more convolution before I get out of here.
Can we bring any equations with us?
Nope. You get only a piece of paper and your pen or pencil, and that's it. And I mean, if it's, I'll be fair about this, I'm not gonna ask you some crazy kind of a functional, to integrate something bizarre, if that's what you're thinking of. Yes, sir.
I assume this will be no calculator like all the.
No calculators, nothing electronic, nothing. If you need a form, I mean, if there's something I feel you should have a formula for, I would give it to you. For instance, integrations, but I'm not gonna, you shouldn't need it. Think about this, think of the quizzes, right? What level of difficulty were they? That's the level of difficulty of the test. Homework quiz is about the section. All right, now I want to do another one, convolution. Here, I'm going to give you two mathematical statements. I'm going to say x of t here is equal to e to the minus 2t, and it's going to be times u of t minus u of t minus 2. And then I'm going to have h of t here be equal to a pulse function, p2 of t. And I want you to convolve that. So, matter of fact, let me do it this way, because this is more in keeping with what I'm after. Let me just have this e to the minus 2t u of t and p2 of t. So this is a pulse, that's an exponential decay, but it doesn't have a value for t less than 0. So my suggestion is you draw one of these. Do you all agree that this one is varying more in time than this one? Do you agree?
Yeah.
So that's the one we don't flip. If we're convolving these two functions, we leave that one alone. And that one looks like this. This is e to the minus 2 tau, u of tau. And that's going to be my x of tau. It does this, like so. And this is tau. Now, when I flip and shift this, what happens? Just think about this. Well, a pulse waveform, this is the one that usually gets people. If this is t here, the pulse has a width of 2, that would be 1 minus 1, that's a height 1. This is p2 of t, right? All right, well, if I make this tau, it looks like this, correct? And if I make this minus tau, it still looks like that. Do you all see that? In other words, p of minus tau is p of tau. It doesn't change its shape, even though this technically rotates to here and this to there. So when I show you this one, this is the one that gets people, by the way. Here's 1, here's minus 1, this is tau, and this is p2 of minus tau, correct? Now I'm going to add t to it. But what I want to do is have it move and start at t equals minus 1, don't I, class? So here I'm going to put t, like so, but I need to move this back. Now what does that mean? That as I'm moving it back, this is really what? This is, isn't this, go ahead and say it, somebody said it.
T plus 1.
This is going to be t, right? Plus 1, and this is t minus 1. Isn't it, class? Right? Now think about this. These are what the bounds are. What happens when t is minus 1? Shifts to here, right? And this would shift to here, correct? So what I'm going to get at, the upper bound here is t plus 1, and the lower bound is t minus 1. So now we can say that we're going to have this effect. But this is going to be for t, right here, greater than minus 1. Just follow me this. Greater than minus 1, and t less than 1. Because the width of this is what? 2. Do you agree? So for a full 2 seconds, it's going to be moving into this. This would be at t equals minus 1. And as time goes by, it rolls this way, and then when t equals what?
T equals
1, then everything is submerged in here, right? And then now we start getting the effect where we've got a moving window inside. How many see this right here? With me? So between this time from -1 to 1, the area of overlap is right here. And it would be from 0 to t plus 1. Do you agree with me? Everybody? So when we take a look at this, when I go from t greater than -1, less than 1, I can say my y of t here is the integral of e to the minus 2 tau d tau. This has a height of 1. Times that, it's just going to be that right there. And it goes from 0 to t plus 1. Does everybody agree with that? Class? All right, now do the integration and you get what? Well, if you integrate e to the anything, e to the minus, or e to the plus a tau d tau, you get 1 over a, right? So you get 1 over minus 2, don't you, class? And then it's going to be e to the minus 2 tau, evaluated at 0 to t plus 1. I just did the integration. There's one thing I like to do whenever I see a minus sign out there. What is it?
It's like flipped it and bounced.
Change the limits. Take the upper limits, put them down here, lower limits up there, and get rid of the minus sign. That's me personally. It saves a lot of anguish because people drop minus signs very fast. So this becomes t plus 1, and this becomes 0. And then I can do it. Now I have 1/2, and I have e to the minus 0 or 1. And then I have minus e to the minus 2 times t plus 1. And that right there is a perfectly acceptable answer when you stipulate it by that. All right, the condition. And that'll be, this is something the grader will look for, is the interval of time. All right, do you all agree with me there? Now, what happens is, this is y of t. I can break this up and I can have e to the minus 2e times e to the minus 2t, but this is fine just the way it is. And this is y of t. Now, after that, I'll stop for 1 second if you're trying to copy this down. I want to make sure in this next point I make clearly. This is a moving window problem. These are typical. You get into these all the time. You've got basically a window of a certain width moving through a function, and you're finding the area of the product of those two functions. Now the next thing I'm going to do is this. I'm going to take this, and now it's completely inside. And this is going to be for time greater than 1. Now what's y of t going to be?
It'll be,
t minus 1, t plus 1.
The limits now have two limits that are functions of t, and that's the key. A lot of times, for some reason, this one gets dropped. But now it's going to be the integral from t minus 1 to t plus 1 of tau, or I'm sorry, of e to the minus 2 tau d tau. And that's going to be minus 1/2 e to the minus 2 tau, evaluated from t plus 1 to t minus 1. Do you all agree with that? And we can go ahead and put in the values and and switch the limits and evaluate it. But you all see what I'm doing here. How many see this right here? Now those are two of the more of the problems I think give people the most trouble. The pulse function does when they flip and shift it, and an offset window gives people problems. But the rest is just knowing convolution, because you can have almost, you know, when it comes to something like this, this could be t times u of t, it could be t squared u of t, it could be something like 1 minus t u of t, or it could have any other functional form that is a practical thing to actually draw. And this pulse function really just takes a chunk of it and the product of a chunk of that thing together, and then get the output. All right, now, before I move from convolution, does anybody have a question about convolution or a problem you want addressed at all? Okay. Convolution is the most difficult concept, I believe.
So, X of t convolved with H of t the same as H of t convolved with X of t, correct?
That's right. It doesn't matter which one you flip or shift. It's absolutely symmetric. And that's important. By the way, you can convolve three functions. And if you convolve three functions, you can convolve any of the ones, the first two that you want. And then the product, once you convolve that, you convolve with the third one. And what's nice to do is if you have a delta function, if you have to convolve three, always convolve the delta function with one of the other ones. Because that just replaces the argument of the other one with the argument of the delta function. All right, now, next Laplace transform. This is something that we did. We spent most of the time in this course so far on Laplace transforms. So when we take a look at Laplace transforms, there's both the inverse and the direct. So if I have x of s, it's defined as the integral from 0 to infinity of x of t e to the minus st dt. That's the actual Laplace transform. If you do the inverse, technically the inverse is x of t is 1 over 2 pi j times the integral from minus infinity to infinity of x of s times e to the minus st, or plus st, and this is going to be the s. But we never use this. When we do, theoretically you could, but what we do actually is what? Partial fraction expansion. And we know, based on those tables that we've used so frequently, what the relationships are. Just to mention a few, if this is x of t and this is x of s, you know a delta function goes to 1. You know u of t goes to 1 over s. You know that t u of t goes to 1 over s squared, and so forth. We could populate a table very quickly, but you've worked with those a lot. So these are common Laplace transforms, right, class? You know. Now, with Laplace transforms, chances are I'm not going to ask you to do just the Laplace transform of something mathematical. Chances are I'm going to give you a circuits problem, so I'm going to go from there. Typically, and we could put an op amp in this one, but for the sake of trying not to get too, well, we can actually. Why not?
Let's do it.
Here, my voltage source is going to be, make it e to the minus 2t u of t. I'll make this an easy, this is fairly common kind of thing here. We'll ground that. Then I'm going to go ahead and put a resistor here. I'll just call it R for now. And it's going to go into the negative terminal of an op amp, the inverting terminal. This one I'm going to ground. And then I'm going to put a capacitor here, C. And this is my output. Say it's V out of T. And that's what I want. And what do I give these values? R is going to be equal to 10 ohms. And C is going to be equal to 1 millifarad. So now I want to find the output. And the obvious way to do this, we could do it with differential equation analysis, but since we have Laplace transforms available, it makes sense to do it with Laplace transforms. So if I take a Laplace transform of this, what is it? Now this is one we kind of, I didn't put this down, but
1 over s plus 2.
1 over s plus a. So for this one, this is going to be 1 over s plus 2. Do you agree? Right?
Yep.
That is 2, by the way. Like, how many agree with me? Help me out here. All right, now we put the impedance in terms of the S domain, correct, class? What's the impedance of a capacitor in terms of the j omega domain? How's that? 1 over j omega times c, and in the S domain you just replace j omega with s. So this is going to be 1 over what? S times 10 to the minus third, or really this is going to have an impedance of 10 to the third over s. Do you agree with me, class? Agree? Over here, that's just 10 ohms. Now, what we can do here is get the transfer function of this right here. So now we can say my h of s is really V out of S over V in of S. I want to do it this way to make sure I cover transfer functions at the same time. Does everybody understand what I'm doing here, transfer functions? This is my input, this is my output. I need really a relationship from V out over V in. And in this case, what is it going to be? Well, we know that the current here would be the input, if it was VI of S, right, divided by R, correct? That current goes into that impedance, right? Which is what? 10 to the third over S, correct? And then with the output is going through the inverting terminal, we know it'll be a negative sign. So when I take a look at this, it's going to be equal to minus 1 over RCS. Does everybody understand that? We've done that problem several times. How many do? I mean, I can go through it. What I can say is that this is a V of S, V in of S divided by R is the current there. How much current enters the negative terminal? Zero. It all flows this way. Therefore, the voltage here would be that current times that impedance, 10 to the third over S, correct? So now I have V in of S over R times S times 10 to the third. And then at that point, I realize it's a plus to minus, right? So the voltage here is actually going to be, that's 0 right here. That's 0. It's going to be 0 minus this product of 10 to the third over S times V in of S over R, or to be negative. That's where that negative sign comes in. And then you divide out the V in of S, and you get V out over V in right there. Now, my output, therefore, V out of S is equal to my H of S times my V in of S, and now I put in the values. Here, I've got R is 10, C is 10 to the minus third, so it's 1 over 10 to the minus second, or 100. So now I have minus 100 over S, right there, times V in of S over times 1 over S plus 2. And that's my V out of S. Does everybody agree with that, class? Take a careful look. Make sure you see it. Everybody? Can you see it in the format? Now, once I have this, I need to expand it, don't I, class? Correct? And when I expand it, I'm going to have, this is two simple poles. I have A over S plus B over S plus 2, don't I? How do I get A?
S is equal to 0.
What I'm going to do is cover up the pole at S here, right? And I evaluate the remainder at S equals 0, right? What is it going to be? Minus 100 over 2 or minus 50. Do you agree with me? I'm going to say this right here. You're mumbling. So this is going to be minus 50 over S plus, and how do I get B?
Cover up S plus 2, set S equal to negative 2.
And what do you get?
50.
Y'all agree with me? All right, that's my output. Still in the Laplace domain to go to the time domain. Did I put U of T here? I did. The basic thing, this is V out of S. Therefore, V out of T will be what? The minus 50 stays, right? It's a scalar. What's 1 over S going the other way? U of T. And what's 1 over S plus 2 going the other way? Right, e to the minus 2t u of t. Now, if I ask you to plot that, this is something you just take a look at. Where does it start at 0? Please take a look. If t equals 0, what is it? It's minus 50 plus 50, or 0. Understand, class? And now what happens as time goes by? This one drops out, and it goes to minus 50. Do you all see that? Yes, sir?
On a test, to save time, would we be able to just recognize that that circuit integrates whatever's put into it and just integrate the input function? Then multiply by constant.
You mean integrating the time domain? Is that what you're talking?
Yes, so from 0 to t.
No, I want to see the steps. If I ask you to use Laplace, I want to make sure. It's the testing of Laplace.
Alright.
All right, this is a fair problem, and it can get progressively more complicated. What can happen is you can have this right here. You could have an inductor here as well, in parallel. Now you would have to write the impedance of that, right? And technically what I should have said is, in general, when you have an operational amplifier circuit, where this is some Z1 and this is some Z2, and this is the output, and this is the input, then technically V out of S over V in of S equal to H of S is equal to minus Z2 over Z1. And this is in the Laplace domain. Do you understand that, everyone? So these could be anything. I could put an inductor, I could put a capacitor in series with a resistor, a capacitor in parallel with a resistor. What you have to understand is this is the basic, we can prove that if we want, but fundamentally, that's what it is, isn't it, class? Y'all remember? Just, this is important. All right, that's something where we use Laplace transforms to analyze really a circuit with a non-sinusoidal input. And if you really, get more complicated, this could be what? This could be t times e to the minus 2t, correct? And if e to the minus 2t u of t is 1 over s plus 2, then t times e to the minus 2t u of t would be 1 over s plus 2 squared. Do you remember that? How many do? Good. Most of you do. And then you'd have to put that in there. Then you would have a double pole to worry about. And you would have to have a single pole and a double pole, the second pole come out and find 3 constants. Do you follow me on this, class? So it gets progressively more difficult, but you can see the steps that you need to take. That's that's an important problem to understand as a circuits problem. Now, a couple others. I want to talk.
Can you do something like duality with like discrete time?
We're not going to have discrete time on this test.
Oh.
All right. If you want it, I'll put it there.
No, you don't have to.
Oh, please put it there. That's what I live for. One time I had a kid that he was really just out of control. He said, "Is this going to be on the test?" "Yeah, I'll put it on." "Sure." "Is this going to be?" "That's a good idea. I'll put that." Finally, shut up. I don't know if he survived the night.
Let's just do the final. Should be like.
And I try to be very fair about this. I was once in your shoes, and believe me, I know that you're trying to anticipate questions. Just remember this, the homework and the quizzes are it. And I look at old tests sometimes and I modify problems, but I'm just going to tell you this right now. I wouldn't waste my time looking at old tests. What I would do is focus on the homework and the quizzes. And that's, ask anybody about me. They're going to tell you that's how I make, out every test I've made since, I don't know, I've been here basically. All right, next problem, or the next thing I want to talk about, you mentioned duality, right? You want me to do we can do a duality problem if you want. Matter of fact, it sounds, yeah, we'll do this because that way, I was going to do Fourier series next to do duality. Suppose I want the inverse Fourier transform of this. Let's do it this way. And this is going to be my x of small omega. All right, so this is a Fourier transform. And what I want is x of t. So how do I get it?
5 by 2 pi.
Pardon?
5 by 2 pi. Or right now.
What you're really after is you're looking for first the definition of this in terms of known functions. That's a starting point. Does everybody see it looks like a block subtracted by a triangle? Do you see that? How many see that?
Oh, yeah.
All right, so let's write this out what it is. So it's a block, in other words, it's a pulse function of width 2, right, of omega, minus a triangle function of width 2 of omega. Do you all agree with that? First, make sure you see this. Show of hands. Now, the next thing you need to say is, do I know something about these directly in terms of the time domain functions? Well, some of you do, and you just said, oh, I know it's just the time domain function, change omega to t and divide by 2 pi. But some people don't know that quite the way, and I like to see it done this way. You should know that a pulse function of with tau of t goes to tau times the sinc of omega tau over 2, and that a triangle function of with tau of t goes to tau over 2 times the sinc squared of omega tau over 4. Y'all remember those, class? And now I go and use duality to get what I want. So from here, I can say, based on duality, I take this function and put it over here, replace t with minus omega, so I put p tau of minus omega, and I have to put a 2 pi here. And then I take this function over here, tau times the sinc of not omega, but t tau over 2. And what can I do with that minus sign and why?
Go over
Get rid of it,
it's
get
the symmetrical.
It's an even function, right? Then I can do the same thing over here. I can take this function over here, make it tau over 2, the sinc squared of omega, of t tau over 4. And then there's a 2 pi here, and it's going to be a triangle function of with tau plus omega, because it's an even function as well. What he just said is right. You divide that by 2 pi. So now I divide both sides by 2 pi. Make that 4 pi here. And now I have the inverse transform of what that's made up of. Does everybody see this, class? Give me a show of hands if you do. I'm not trying to work too fast, but I only got a minute here, minute and a half, and I haven't done a FOIA yet. You with me? Now, you all see that what this means is when I do the inverse of that, tau is just 2, and you take, this one would be, what? 1 over pi sinc of t, really just t, because tau is 2, and it's going to be minus, and this is going to be what?
1/2 of pi. Yeah, 1 over pi.
It's 1 over 2 pi, right? And it's going to be sinc squared of really 1/2, right? T times a half. But I think you can handle that, all right? So let me just make one comment about the Fourier series. So the thing that I've told you over and over again, the thing I like to see is people making use of that derivative method I showed you. How many remember that? All right, you're going to get that a problem, probably something very similar to what you've had already, where you're going to have some periodic waveform. And it could look, it might look like this. And call this 2, call this 1 3/4, 1/2, or maybe 1/4, and then 0. Well, anyway, I'm just going to say that this is 1 here, and this is my x of t. It's periodic. The period would be 2. You got to capture that. If period's 2, omega naught is is t, right, over 2 pi. Correct, class? So you'd have omega naught, the fundamental frequency. After that, this x of t would be represented by an actual series. Right? N equals minus infinity to infinity. We could get c of n there by an integration method, right? But we don't want to do that because it takes too much time and there's integration by parts. We take one derivative. What do we get with one derivative?
Go and get a constant slope, 0, and then constant slope.
Do you agree with me, class? And then we take another derivative. Do you agree? And what do you get with another derivative? Impulses, right. When you get x double prime, now I have this, then I have this, and this. And then you could get the c of n double prime, correct, class? Show of hands here. After you have c of n double prime, I got 2 derivatives to get there. I would divide c of n double prime by j n, or by j n omega squared, right? and then you would have C of N. All right, I think you understand what I'm getting at. Please make sure you get through your sleep for this exam. I know it's at 1 o'clock, but I can't tell you how many people, when they're sleep deprived, make insanely stupid errors. I mean, 1 + 1 is 11, stuff like this. And that happens all the time.
Isn't